So getting into, again, the way that we see it. So if we take a luminous object, an object that is luminous is something that makes its own light. So think a flashlight, a light bulb, your wherever you have lights in your house, right? Those are going to produce their own. Big scale, we're talking stars, right? So something that produces its own light is a luminous object. And the color that we see of that object is based on what it makes. So if you see something, so if you have a light that's blue, right, there's either a blue color on it or it's actually producing a blue light, such as a laser, right? I mean, a laser, shine a red laser, that's producing red light. Shine a green laser, that's producing green light. And the way that we can then get every other color is by combining in some variation red, blue, and green. Right? Those are what we call our additive primary colors of light. So our primary colors in physics when we're talking about light is red, blue, and green. If you take a red light and a blue light and combine them, you get magenta. If you take a red light and a green light and combine them, you get yellow. And if you take a green light and a blue light and combine them, that means you get cyan. Take all three colors in equal quantities, you produce white light, because that's what our eye perceives. So depending on what colors you have and what you're trying to find, like for example, if you have a light that is magenta, our eyes are getting equal stimulation of the red cones and the blue cones. If you have a cyan light, that is sending out blue and green to our eye. Our eye picks up the blue and green. We see the cyan. If we take yellow light and then add blue light to it, you're going to get white. Because to produce yellow light, you need to have red and green. That's going to make your yellow light. Add in the blue, that's then going to produce white. Now, if you start varying the amounts of these and you start changing the intensities of the lights and you kind of let one color dominate more than the other, that's where we're going to get different shades and different colors. That's where we're going to get our oranges from, right? So some of those colors that are also going to exist. Now, things change when we look at an illuminated object, right? So an illuminated object is something that has light hit it, so it does not produce its own light. So you're talking, clothes and paint on a wall and the fabric of a chair, right? Those sorts of things that they don't produce their own light. And what we see on an illuminated object is the color that it either reflects or the color that it allows through. That's going to be known as selective reflection or selective transmission. So our subtractive primaries of pigment are cyan, magenta, and yellow, which, if we go back to the previous slide, are the colors that we can mix to create here. Also note the red, blue, and green. If you look at any electronic device, so the screen on a laptop, the TV screen on a smartphone, right, whatever it is, when you change your color settings, you're changing red, blue, and green. Right? Those are the color settings. So every LED that exists on that screen is only producing those three colors. Again, it doesn't actually make yellow. It just makes it makes a sea yellow by combining the red and the green. So if we go here, right, we look at what are now known as our subtractive colors of pigment, right? So our pigments are dyes, right? Things we can use to produce other darker colors. Because as you mix pigments together, things get darker. When you mix light together, things get lighter, right? So when we think subtractive, the more you add, the more you combine, the more you combine the pigments, you're actually taking color away. Whereas when you combine light, you're adding it together. So cyan, magenta, and yellow are subtractive primary colors of pigment, which are your three colors in a color printer, right? That's what we use to print with. Same idea here when we start looking at pigments. What you see is the result of combining those wavelengths and intensities, right? So if we start modifying the amount of yellow and the amount of magenta, we're going to get different shades of things. Equal amounts magenta and yellow pigment are going to produce red. Equal amounts cyan and yellow will produce green. Equal amounts cyan and magenta will produce blue. If we start mixing all of those in equal quantities, we eventually get to black. Now, an illuminated substance, right? So if something is receiving light, we have three different behaviors that light can do. that light can reflect, which means that light's going to hit the substance and bounce right off, right? It's not going to be accepted. The light could be absorbed, which means that light hits it. That light is then taken into that material, and that energy is converted into something else. Usually it's converted to heat. Again, think about in the summer, you'd rather wear a white shirt than a black shirt because everyone goes, well, the black shirt gets warmer, and it's because it is absorbing every single wavelength of light. When you go outside, the sun hits that shirt. Any part of the shirt that's black is absorbing all of the light. There's no light that's reflected off of that black shirt. So because of that, the energy from the light converts to heat, which makes you get warmer. Transmission is the last one here, and that's where that light can just pass through. Now, we have three different types of substances. We have opaque, translucent, and transparent. Again, these are illuminated substances here. Opaque would be the one on the left. Light is either going to reflect or light is going to absorb, right? We're not going to see transmission actually happen here. It could be translucent. And when it's translucent, right, so we're going to get some transmission. That light's going to pass through it. However, the light's going to scatter. And that scattering is going to kind of give that foggy appearance where you can see through it, but it's not very clear. Some light will still reflect, some light will still absorb. And then we get transparent, right? So think about a window, right? An awesome window is going to be transparent. That light's going to go through, it's not going to scatter. What we see behind it is going to be nice and clear and easy to see. We're still going to get some reflection, still going to get some absorption, right? If you go to a window in the summer, the window is going to be warm, so we still get some energy happening with absorption. And if you look into a window, you can still see a reflection a little bit. So again, not all of that light is going to perfectly go through a transparent window. So based on the behaviors and based on the types of substances, right, we can get either selective reflection or selective transmission. Now, a selective reflection only happens on an opaque object because opaque doesn't let any light through, which means all of that light is either absorbed or all of that light is reflected. So when light hits that surface, it's going to do one of those two. The light that is absorbed has the proper quantity of energy, right? So the quantized energy the light has an acceptable amount that material is going to absorb, and it's going to convert that energy to heat. The rest is going to be reflected. If it doesn't have the proper amount of energy or the right wavelength or the right frequency to be absorbed, it hits the material, it gets reflected, and as a result of that, that's the color that we see. So when you see a shirt that's red, it's because every wavelength of light is being absorbed except for the red that's reflected and coming back to you. If you're wearing a green shirt, right, you send white light at that green shirt, it's going to absorb the reds, it's going to absorb the blues, but it's going to reflect the greens, and that's what we're going to see. Selective transmission is a little bit different. Think transmission, your ability to that light can pass through. So this is going to be transparent or translucent objects. This does not apply to an opaque object. So some light is going to be absorbed. Light that's not absorbed, we're going to pass through. And the color that we see is the color that it actually allows to pass. Think of a color filter here. If you hold up a green color filter, light that's hitting it is getting absorbed. The light that doesn't get absorbed moves through, and if it's a green filter, we're going to see green wavelengths. Right? So our eyes are going to pick up the color green because that has been allowed to pass through. So because of that, the filter takes on that color. If we have a magenta filter, so if we send a white light to it, gets that magenta filter, we see the color magenta because it is letting red and blue wavelengths through. Because our eyes, when they perceive the color magenta, see equal parts blue and red. Because of that, it is a magenta filter. Those two wavelengths of light can pass through. This color triangle here, this color compensating triangle, is a nice way to look at all of this together here. So the primaries of light, the additives of light are on the corners, so red, blue, and green. The subtractives of pigment are along the segments, so magenta, cyan, and yellow. So what we see here is if we have red and cyan, if it's red light and cyan light, mix those together, we get white. If we're talking pigments here, red pigment and cyan pigment, mix those together, we're going to get black. So as you work across, you're going to produce either white or black, depending if you're talking about lighter pigment. And if you're working from one corner to the other, so like red to green, for example, if you mix red and green light, you get yellow light, which is in the middle. If we're talking pigments, so let's say you take cyan and yellow pigment, the one in the middle there is going to be green, so that's where we produce the color green pigment from. And here we just see again as we mix, right? So as we mix things, we get our cyan light by mixing green light and blue light. We get magenta light from red light and blue light. When we talk about our pigments, our paints and whatnot, if we have yellow and cyan pigment, we get green. If we have yellow pigment and magenta pigment, we get red. And so that's going to be the color that we then perceive.